So hi everyone and welcome to this video on integration by the use of partial fractions, but under a case wherein the denominator has repeated factors. So if you recall our last video, we discussed integration using partial fractions, and we said that it essentially is a technique of integration that can be used when the integrand that we have is a bit more complicated, and it's a relatively more nuanced rational function, which we decomposed as a possible sum of partial fractions. Right now, there could be a case wherein the denominator has repeated factors, and when the rational function, okay, has repeated factors, those repeated factors must be decomposed into the sum of the number, so the order. Okay, so say it's 2, so it must be the sum of around 2 partial fractions, one for each of the powers of x minus a. And I think we'll be able to see this clearly with the example. So after decomposing it into partial fractions, we can use our typical methods of integration afterwards. And ideally, this method of decomposing a rational function is easy to use when, again, the degree of the numerator is less than the degree of the denominator. So that's our theory behind this particular method. So let's go to an example. Say we have this example, the indefinite integral of 3x plus 5 over x cubed minus 2x squared plus x dx, right? So we can, what we can do first is, step one, we can rewrite the integrand. So the integrand is 3x plus 5 over x cubed minus 2x squared plus x. We can rewrite this denominator, right, as x. So we can factor out x. Then this is x squared minus 1 squared. Because if you factor it out, it's going to be x squared minus 2x plus 1. And you can break this term down into 2. That's x squared minus 1 squared. So this thing here, that's equal to this term. So we have that there. And what we need to do is we're going to break this down. We're going to decompose this into the partial fractions. And this is where the repeated factors come in. Notice that we have an order of 2 here, so we would need to do it for each order. So we will have a partial function that's a partial fraction that's a over x plus b over x minus 1, that's the first power, plus c over x minus 1 squared, that's the third power. Right, so that's now our decomposition. Then what we're gonna do is we're gonna multiply both sides of the equation, okay, by x times x minus 1 squared, or that's your factor denominator. So we're gonna multiply both sides by x times x minus 1 squared. So that's gonna be so let me just rewrite. So this is 3x plus 5 over x times x squared minus 1 squared equal to a over x plus b over x minus 1 plus c over x minus 1 squared. Then I multiply both sides of the equation by x times x minus 1 squared, and I'm going to get 3x plus 5 equal to a times x minus 1 squared plus b times x minus 1 plus c times x, right? And that's the form that I'm going to have. Then what we're going to do with this form is we can now see that it's in linear form. Then we can think of essentially the values, okay, that will eliminate the terms that we have. So we want to eliminate a, b, and c, right? So it's easy to solve. So we're going to think of the values there. So let me just rewrite this one here. Okay, so let me rewrite. So this is going to be 3x plus 5 equal to a times x minus 1 squared plus bx x minus 1 plus cx. We're going to think of now values for x that will eliminate the term. So I can immediately think, if you look at this, if x is equal to 1, okay, notice that will eliminate, a and b, right? That will eliminate a and b. And if you also notice, if x is equal to 0, that will eliminate b and c, right? Because if I plug in 0 here and I plug in 0 here, that will eliminate the two terms. So we'll work with that. Okay, so when x is equal to 1, we get, so that's 3 times 1 plus 5 equal to a times 0, right? Because we plug in 1, so that's now 0, plus b times 0 plus c times 1, right? So we get 8 equal to c, right? So meaning c is equal to 8. So that's one of the terms solved out. Then when x is equal to 0, okay, when x is equal to 0, we get, so we can get a 3 times 0 plus 5 equal to a times negative 1 squared, that's just 1, plus b times 0 plus c times 0, right? Then we can just solve, so this one will cancel out. That's going to be 5 equal to a. Therefore, we have our second factor. Then, since we know a and c already, we can substitute just to solve b. So, plug it into this form, right, for b. So we can solve it as 3 times, say for example, say anything, x equals 2, say for example. So that's 3 times 2 plus 5 equal to 5 times, so a is 5, right? So that's, if I plug in 2, that's 2 minus 1 squared, so that's 1, plus b times 2, right? 2 times 2 minus 1, that's 1, plus 8, okay, that's c, times 2, right? And what we'll notice is this one will be 6 plus 5 equal to 5 plus 2b plus 16. If we simplify this, b is going to be equal to negative 5. So we now have a term, okay, for each of our given, okay, and we're going to notice that this integrand here, okay, so this 3x plus 5 over x cubed minus 2x squared plus x, we can rewrite this as 5 over x, right? So this is a, plus b over x minus 1. So b is negative 5. Okay, so we can just change this operation to minus, right? So this is minus 5 over x minus 1. So this is b. Then we have c, which is 8. So that's plus 8 over x minus 1 squared. So this is c. Then we can perform now the regular integration that we want. So if we want to get the integral of this, then this is just equal to the integral, okay, of 5 over x dx minus the integral of 5 over x minus 1 dx plus the integral of 8 over x minus 1 squared dx, right? Then I can plug things out, right? So that's going to be 5 integral 1 over x dx minus 5 integral 1 over x minus 1 dx plus 8 integral 1 over x minus 1 squared dx, right? So I have those. Then I can simplify. So the integral of 1 over x, that's just ln x, right? So that's 5 times ln of x minus the integral of 1 over x minus 1, that's just ln x minus 1. So that's 5 ln x minus 1 minus, we have here 8. Okay, so the integral of that, that's just going to be 8 over x minus 1, right? Plus c, right? So plus c. And this is our solution to this integration problem. And that's our simple example on how to do integration by the use of partial fractions when there are repeated factors. So in the next video, we're going to discuss about improper integrals, and I'll see you then. Thank you for your attention.